Good morning all. This is Satish Kumar, Assistant Professor of EC Department. Now let us see the case study on 5G signal quality testing. The problem is how to measure signal quality in 5G private networks. The promise of 5th generation mobile networks is ubiquitous telecoms and a platform from which the innovations can exploit breakthrough levels of connectivity. Full readiness will require several technologies to be developed, presenting some complex testing challenges. Reducing unwanted radio signal interference will be critical for maintaining device connectivity, but no matrix was validated as capable of providing accurate measurements of signal quality. These are the device which used to measure the 5G signal quality testing. Next, challenges. The promise of 5G is revolutionary advance in mobile device user experience, sufficient to drive a transformation in personal connectivity and form a platform for new market opportunities. 5G is less of a technology platform, more a performance specification defined by low latency, multi-gigabit per second data capacity, low energy consumption and seamless connectivity. Yet, if these promises cannot be delivered at tolerable cost, the long-term marketability and returns on investment in 5G will be comprised and potential economics and social benefits impaired. For device developers, the complexities for implementing technologies amplify some challenging measurement requirements. For example, massive multiple input, multiple output base stations can include hundreds of antennas to serve higher densities of connected devices than possible with previous generation technologies. Signal to noise ratio is used as a metric of radio signal quality in device testing, but for 5G, signal quality is more influenced by interference between devices than equipment noise, making this matrix impractical. Signal to interference plus noise ratio becomes more representative, taking account of noise, interference and signal strength, but no traceable definition was developed suited to all 5G devices, including massive multiple input, multiple output systems. Next, solution for the challenge. The methodology for 5G communications define and develop traceable, cost-effective and efficient methods for measuring over the air signal quality. After consulting with industry, existing and newly devised definitions of SINR were evaluated in 4G and 5G simulated systems. The measurement combined validated traceable channel power and error vector magnitude as practical predictors of SINR, as a field trial validated SINR and an accurate and reliable metrics for 5G accessing signal quality. Traceable channel power and EVM are parameters relating to differences in signal modulation errors between device decoders and reference signals. Based on the new assurance in the validity of a channel power and error vector magnitude measurements and recognition of the resulting paradigm shift in testing, it chose to educate the market by the gradual introduction of new signal measurement capabilities. Keysight released its modulation distortion software for the PNAX vector network analyzer, provided calibration of vector network EVM measurements. It later released its first signal strength and channel power measurement capability for over-the-air testing as an handheld microwave analyzer. Keysight is an important participant in the following of metrology of RF exposure from massive multiple input multiple output 5G base station, impact on 5G network deployment, that is developing guidance on traceable radio field strength measurement methods. Practical and cost-effective 5G signal testing and device development will boost the competitiveness of Europe communications sector with support for deployment, increase its potential for transforming mobile connectivity. Now let us see the conclusion. The methodology for 5G communications defined and developed practical and traceable methods to measure SINR over a wide frequency range. It also developed as a broadly applicable definition of SINR for potential 5G and coding schemes to improve metrology for traceable MIMO antenna systems. 3 new 5G MIMO test beds were constructed, one capable of MM-wave massive MIMO communications providing remote access, so developers can simulate connected and over-the-air device testing without leaving their facilities. Second is the availability of test beds enabled traceable test methods and algorithms to be developed, overcoming significantly increased system test complexity arising from multiple antenna elements and operation of MM-wave frequencies. Next one is it also be developed traceable test methods for 5G communication devices supporting vastly increased number of users and device densities. Thank you.